So before we get started on part 2 of this video, I just wanted to show this graphic titled Windows and AD. What it says here is in Windows/Active Directory, there is one system responsible for making access decisions in nearly all cases, the Security Reference Monitor. This system makes access decisions by analyzing security descriptors on securable objects and user rights assignments. So as I finish up reading this article from Microsoft in 2008 titled Access Control Understanding Windows File and Registry Permissions, which the link is right there if you wanted to read along. Before we get really far there, I just wanted to show a graphic that really helps me understand things a bit better. Here's user rights. Down here is security descriptor. So analyzed by the Security Reference Monitor. Ultimately, that is what's controlling access to whatever securable object we're talking about. Okay, so we're going to go ahead and get started here. If you Control F from that link down below, you could type in Windows Resource Protection as you're seeing in white right up here. So they say starting with Windows Server 2008 and Windows Vista, components declare their needed security settings in their manifests, which are assigned by a Microsoft code signing root. The manifest specifies the ACLs and other permissions associated with the file. Thus, when a component is installed, it carries with it the appropriate security settings. In addition, OS files are protected from inadvertent damage by the system administrator using Windows Resource Protection, or WRP. It says route up here when it should say root, and down here says warp instead of WRP. Anyways, this Windows Resource Protection relies upon a new system-level entity, Trusted Installer, to own and manage system files and folders. And just note here that Trusted Installer is a proper noun, so both the T and the I should be capitalized. And the next paragraph says, a good facility to allow normal users to perform installations of authorized components was added in Windows Vista. Thus, the power user role is no longer required, and instances of ACEs that contain the power user SID were removed. The power user group still exists, but the component manifests have been scanned and all detected instances of grants to PU have been deleted. Let's look at a system directory to see the new permissions. This is also another good exercise in SDL reading. So I did a quick copy and paste here, but still it's difficult to read. Not sure this is much better, but let's try to follow along with what they're saying. Trusted Installers SID is, and then they list it out. Using TI as shorthand, we find the following. So sure, you could see TI here, over here, and if you scroll through, you can see if it shows up anywhere else. Well, interpreting this, you see it is a protected ACE that is being applied to this location using the Windows NT 5.0 inheritance model. Alright, because that's what the I stands for here. Trusted Installer is granted full control over this location and is granted generic all over all child containers under this location, since it is CI inherit only. System and admin are granted read, write, append, read EA, write EA, execute. Okay, so they are going to keep listing things out. This is generic all minus write owner and write DAC. Admin and system are granted everything but the ability to change the owner or the ACL. BA and SY have generic all over child file and directory objects. So definitely easier, I think, to read it on this screen for anyone who cares. There's a SID, here's a SID, there's system, another one, then BA, BA, BU. They go on to write, since the admin has the take ownership privilege, he can still assert right ownership and take control away. Administrator and system are a security equivalent. But with this privilege, a determined administrator can circumvent the WRP ACL controls. What's WRP stand for again? That's Windows Resource Protection. The next paragraph says CO also has generic all over child file and directory objects. Built-in user has read EA. Okay, I'm going to skip that list again. They go on to say all system files and folders have protected ACLs that granted trusted installer full control. The control of files by trusted installer is not expressed in the declaration on the system root directory, but in the separate declarations of the Windows components, plural. The next section is titled Setting Safe File System Permissions. Now that you have some idea of how file system ACLs work and how to read them, let's look at setting them. If you are installing an application, you should install this to the default program files location. The default ACLs for this location give full control to administrator and local system, which is appropriate. If you install an application to some other location or grant the user the ability to choose his or her preferred location for an application, you have a problem. The default ACLs for other drives and for non-system and non-application areas of the system drive are not secure enough. In such cases, you must explicitly ACL your folders with the appropriate protected DACLs. Or pronounced DACLs. The simplest and safest choices for installing on application is to duplicate the security settings on the program files folder. If you choose not to do this, set the DACL so that non-administrators cannot change DACLs or ownership of executables and cannot write, append, or delete files in directories containing executables. The basic rule, if you are setting DACLs, DACLs, is that you do not want administrators or other users executing code that was written by a user. This is a particular problem if the folder in question would be presumed to be trusted. Yeah, see, I'm just going to have to spell out DACL or else we're going to get some weird spelling like these two that you probably see my cursor highlighting right now. So anyways, yeah, they're saying this is going to be a problem if the folder is in a trusted area, such as Windows, program files, and so forth. Doing so allows elevation of privilege to administrator and increases the risk of cross-user attacks. Thus, if a user can write files to such a folder, other users and administrators should not be able to execute them. At first glance, it would appear that you should not let users write to folders in Windows, system, program files, and so on at any time. It turns out that there are valid reasons for doing so. The most common is to record error log data. If the executable is running under the user's credentials and has to log an error, it needs write append access to the error log logging folder. If you logged errors to per user locations on a multi-user system, you would have the logging data spread over the system instead of being associated with the executable. Applications and services typically write to a shared folder or registry key. You'll find the same issues in the registry where error information is frequently stored in specified machine registry keys by a process running with user permissions. Do not mix user writable files with executable files. Use separate directories for files that must be trusted, such as executables, and files that must not be trusted, anything potentially written by an untrusted user. ACL the directories appropriately so administrator control over the executables and user read write or read execute, but not write. The same guidance applies to registry keys and subkeys. Now, client and server differ here. Server administrators are assumed to be far more knowledgeable than users running as administrator. Server administrators know that they must not execute code from untrusted areas of the system. By establishing a naming convention to isolate data files from executables in the system, you provide the administrator guidance concerning the trustworthiness of the executable. Logging subdirectories are not trustworthy, thus users must not have the ability to create or modify these subdirectories. as this would enable them to spoof safe naming rules. In the client environment, it is far easier to fool the administrative user into executing code. With such naive administrators, directories that have user right must not allow administrator execution privileges in order to prevent a user from installing an executable and then fooling an administrative user into running it and compromising the system. For example, if your application or service needs to store log information that will be written to under user privileges, you should create a logging subdirectory to hold this data. This subdirectory should not allow admin execute. One way to do this is to add a leading explicit deny for a file or for file execute to everybody, and then that's the example they give. This prevents cross-user attacks in directories that allow file write or modify to users. There are many cases where it is expected that users will share data, though we do not want users sharing and executing code from a shared area. For example, a home user or his photo viewing application is likely to create a folder such as See Photos. The user expects to be able to allow multiple users to to write to this folder and have multiple users edit the various photos in this folder. The default ACLs on the root of the system drive on Windows Vista supports this. The other common sharing situation is a folder in which users place data for other users to read. Only the creator of the data is allowed to delete or modify the data, but other users may copy it and then edit the copy. This is a shared read scenario, and it is the default for the system drive on Windows Server 2008. Consider the case where you choose to lock down the system drive and specifically ACL folders for sharing. You have to choose the ACLs that are appropriate for these two rather common scenarios. We want administrators to be able to manage objects, and we want to prevent security issues associated with execution of the code in these folders. And note that the ACEs here prevent even the owner from executing from these folders. So here's a shared read ACE, and then in red I've added a collaborative ACE. Note that both ACLs start with a deny execute ACE for everybody. Object inherit to apply to files to prevent user system and cross-user attacks. Then administrator system does not really need it, and CO are given full control equals file all. So you see the FA in the variety of locations here. For the shared read scenario, an authenticated user is granted list, add file, add subdir, read EA, traverse. Okay, I'm not going to read the rest of the list. I want to put it here for you though, so it's in white. And so we can move on to our next section here. It's titled Managing the Registry and its Permissions. So Windows stores much of its state information in the Windows registry. Registry data stores are known as hives, where data is stored in keys and subkeys, which are both viewed as containers. Subkeys are not viewed as objects. User-specific data is stored in the appropriate user section of Hive key users, so HKey_users, as one would expect. Much of this data is writable by the user. If any session, that is HKey_current_user, HKCU, points to the appropriate section of HKey users. System and machine information is stored at the HKey local machine, so that is HKLM Hive. Included in HKLM is information for all the various system services, most of which now run with limited permissions under either the various local service or network service groups. Services and applications can store state information in their registry keys. This information should be stored in subkeys, either in the service key or in a key under the service key. The service key must not be ACL, so I made that word a word that's in the past tense. So the service key must not be ACL'd to enable the service to have set key over its own service key, or the WDAC or WOWN, which would enable such an attack, as this allows the service to point to a different executable. Such an error introduces a potential EOP, elevation of privilege is what that acronym stands for, against the service host, as the service control manager will load the executable that is pointed to when the system loads. The general guidance for DACLs for HKLM is that they must not enable users to write or modify this data or the associated ACLs and ownership. As with the guidance on setting file system DACLs in system areas, exceptions occur for error logging where an app or a service running under a user or limited context needs to record error information. The guidance for such situations is similar to equivalent issues in the file system. Create separate keys for such information and ACL them appropriately. Thus, the sensitive information can be ACL'd to trusted subjects, and the logging data can be writable as needed. The situation you are trying to avoid is a user modifying trusted parameters, such as turning the antivirus or anti-malware service off, or tampering with a tool that users or administrators use. Let's assume that when Notepad is invoked, it loads the Notepad executable located in the Windows folder on the C drive. Well, the default ACL over this location does not allow an attacker to modify the executable. If the attacker can rewrite the link from the Notepad icon to its executable, the attacker can cause a different file, say rootkit.exe, located in a tools folder on the C drive. This could load a rootkit and then load Notepad so that the user would not be aware of the compromise. If the attacker can drive the link through the registry, the protective ACLs on the file system are immaterial. You are concerned with attacks from limited system services against other system services as well. In Windows Vista and Windows Server 2008, services are separated into groups by the privileges they need. The defense in-depth protections offered by this service isolation require configuration of the service permissions so that services cannot tamper with one another, particularly across service groups. Just as we are concerned with preventing users from adding or linking to malicious executables, we must also prevent services from having the ability to change their permissions and capabilities. The change conf, so CONF privilege, on services must be restricted to administrator, system, or trusted installer, since this privilege allows the possessor to change the permissions on the service. Alright, so that privilege, I rewrote it up here and underlined it. So now we're in the wrap-up section. They write, Windows provides a very rich set of permission controls that can be used to permit operations, block operations, and provide defense in depth against new threats. Unavoidably, associated with this rich ability to control access is the issue of complexity. Following a few general guidelines will help you avoid problems. For instance, the system defaults are reasonable compromises. You should use them. If you are installing an application outside of program files, use the program files ACLs. In some cases, you may want to tighten defaults a little bit, such as the default grants to users on drives. But remember that if you indeed do this, you must be prepared to look for and deal with potential application compatibility issues. The most important guideline is that administrators or system accounts must not execute code or follow pointers to code that a user can write or modify. That is such an important sentence to me, I just pasted it right in here. Almost as important is that users not execute code or follow pointers to code that another user can write or modify. These guidelines drive all of the security issues discussed here. If any changes you make follow these guidelines, you have avoided the most serious security issues. For more information about access control components, they give you a link. Okay, so I put that link right here. Information about the ACE string access mask components can be found at this link. Okay, so I turned that one red actually. And when you go there, this includes pointers to specific rights for files, directories, registry keys, shared sections. Now this part of the video, this is the figure A we read about in part 1. So it's near the top of this article. So here are standard rights, hex token permission, then figure B is specific rights for files and directories. This might look better. So figure B, figure C, and you might need a pause here, figure D, figure E. I don't want to go too fast and screw up your ability to pause. Figure F is specific rights for Windows stations and desktops. Figure G, specific rights for symbolic links and events. Here we have rights for semaphores and mutexes. Then we have specific rights for pipes and tokens, common or well-known accounts, and their SID strings. So DA is domain admins, and I did a bad job if you were trying to pause and read any of these. Just going to the link might be your best bet. And so we'll end the video real quick by talking about the author, John R. Michener, Senior Security Program Manager for Microsoft. He joins Windows Security at Microsoft almost 5 years ago. He has 20 years of experience. And you can email him if you want. Thanks for watching.